All right, so now we're going to look at combinations of functions. This is something, again, you've done this before. You may not have realized it, but actually a lot of things that we deal with are combinations of functions, technically. So let's jump right into it by warming up a little bit. So first, if I give you f of x equals 3x squared minus 5, I want you to evaluate f of negative 2 and then state what does that represent on a graph. So pause the video, do that. That's something we've done before. That was a while ago. And unpause when we're ready to discuss. Okay, so hopefully you plugged in negative 2 and you got an output of 7. So we have f of negative 2 equals 7. And what does that represent on a graph? Well, remember, the 7 is a y-coordinate or a height of a graph, and it's telling us that when x is negative 2, the y-coordinate or the height is 7. So we have the point negative 2, 7 on the graph. Now you might be asking yourself, well, why are we doing that? That's not what you said this lesson was about. Well, it kind of is a big part of this lesson also. So we want to make sure we recall what it means when we see this notation f of negative 2, and also what does this represent graphically as an answer. All right, so here is combinations of functions. The biggest challenge to this is going to be notation. The actual operations that we're going to be doing are pretty basic because it's addition, subtraction, multiplication, and division. So we want to understand that this notation and this notation are the exact same thing. This notation and this notation are the exact same thing. This notation and this notation are the exact same thing. And this notation and this notation are the exact same thing. And then here we can see examples of this. So combinations of functions. I can be adding, subtracting, multiplying, or dividing the functions. So if I have a function f of x equals 5x and g of x equals x plus 2, if I see f plus g of x, this is going to be literally 5x plus x plus 2, which is 6x plus 2. If I see f minus g of x, this is 5x minus the quantity x plus 2, so don't forget to distribute the negative, and so this becomes 4x minus 2. F times g of x is 5x times x plus 2, so distribute, and we get 5x squared plus 10x, and f over g of x is 5x over x plus 2. Remember, that's what the x here is just telling us that is the input to the function. It's the same as when we write just our function notation f of x, right? This isn't saying do f plus g and then multiply that answer by x. It's just saying that I have f of x plus g of x. They are both functions of x. Okay, so that's combinations of functions. Literally, that's what we're doing. Now, the reason that we did that warm-up, though, is think about what is this actually saying? Well, the output, whenever I have f of x, remember that represents a y value. And so when we are adding these together, or subtracting them, or multiplying them, or dividing them, what we are literally doing on a graph, and we'll see this a little bit later, is we are adding, subtracting, multiplying, or dividing the y-coordinates at the x-coordinates. Again, if that's confusing, we'll see that later. So first, we just want to make sure we understand this notation, so that's what we're going to practice first. All right, so we're going to do the simple one together, and then I'm going to have you practice some on your own, and we'll talk. So first, here I have f of x equals 3 root x, g of x equals negative 10 root x. I want to find f plus g of x. I want to state the domain of that function, and then I want to evaluate the sum when x is 4. Whoa, that's a lot. Not really. We can do this. So f plus g of x, remember, this is just saying find f of x plus g of x, and so that is going to be 3 root x plus negative 10, sorry, forgot to write the 10, negative 10 root x, and we know from before 3 minus 10 is negative 7 root x. So f plus g of x is negative 7 root x. That's the first part. We'll highlight that in green. There, that's lovely. Okay, then the domain. Well, there's two ways we can approach this. One, we can ask ourselves, well, what is the domain of a square root function? Well, the domain of a square root function is 0 to infinity. The negative 7 is going to be a vertical stretch and a reflection, but it's not going to change the domain. It will change the range. Another way to think about this, so the domain of f of x is 0 to infinity. The domain of g of x is also 0 to infinity for the same reasons I talked about before. I'm not going to go into great detail on this because this is something we did earlier in the unit, but we know that, again, the domain of a square root function is 0 to infinity unless there is a horizontal movement. This is a vertical stretch, so that doesn't change it. So both of these are square root functions. This, again, is a vertical stretch and a reflection, so that is not going to affect the domain. So then if I combine the two functions, that doesn't change the domain, right? If they're both 0 to infinity, then the result is 0 to infinity. So my domain here, we could graph this as well if we needed to help us with that. But if, again, going back to the graphing of these functions that we did earlier in the unit, if I understand the domain of the parent function, it makes it a lot easier to understand the domain of a transformation, or in this case, a combination. Because a combination really is a type of transformation also. Okay, so that was the domain. So now then the last part is evaluate the sum when x is 4. So just in terms of notation, this is really saying find f plus g of 4 now. But we already know f plus g of x, so this is negative 7 root 4. And that becomes negative 7 times 2, or negative 14. So f plus g of 4 is negative 14. All right, nice work. Oh, and one other thing with the sum part, we could have also plugged the 4 into the original part when we did the combination, right? And it should still work out the same. So just keep that in mind, that when we're evaluating at a location, it doesn't matter if we do that after the combination here in the green or before the combination here in the red. It should be the same either way. All right, now I'm going to let you loose a little bit. I want you to try and do this one. You're doing f minus g of x, where f of x is 3x to the third minus 2x squared plus 5. G of x is x cubed minus 3x squared plus 4x minus 2. You are identifying the domain of this, and you are evaluating the difference when x equals negative 2. You can do this. Pause the video, unpause when you're ready to check. Okay, so here, assuming I didn't make any mistakes, which can happen, f minus g of x is 2x to the third plus x squared minus 4x plus 7. The domain is all real numbers, or negative infinity to infinity. And f minus g of negative 2 is positive 3. Now, just a couple of quick things on how I got that if you were confused. So first, when I do the subtraction of the two functions, and remember this notation here is the same as this notation here, the biggest challenge with subtraction is make sure to distribute the negative sign. So that's why I first wrote this out with these parentheses around the f of x and the g of x, because that helps me remind myself to distribute the negative sign. And so then, in the next step, in the blue, I got rid of the parentheses, and this became minus x cubed plus 3x squared minus 4x plus 2 because of the distributing of the negative sign. Then I just combine like terms, and that is how I came up with my answer. Domain. So for that, again, here I identified the domain of f of x and g of x. However, the biggest thing is these are both polynomials. And we learned in our polynomial unit that all polynomials have a domain of negative infinity to infinity. So the combination of them is still a polynomial. Domain is negative infinity to infinity. Then for f minus g of negative 2, just plug in negative 2 carefully, type that into your calculator, or do the mental math, and we get positive 3. All right, next one. Again, I want you to try this on your own. So f of x is x squared, g of x is square root of x, and then I want you to do f times g of x. Identify the domain, evaluate the product when x equals 9. Pause the video, and pause when you're ready to discuss. All right, so multiplication. F times g of x is the same as f of x times g of x, so I'm literally multiplying these together, so x squared times the square root of x. So I rewrote square root of x as a rational exponent so that I can combine them. And so remember, if I multiply the bases and they're the same, then I can add the exponents. I did this addition off to the side just so we make sure we're comfortable with the addition of fractions. So 2 plus 1/2, get a common denominator. 4 over 2 is the same as 2. 4 over 2 plus 1 over 2 is 5 over 2. So I end up with x to the 5 over 2. So f times g of x is x to the 5 over 2. Now domain. So domain is a little bit different for this one. Domain of f of x is all real numbers, or negative infinity to infinity, because this is a polynomial. The domain of g of x which is the square root of x, is 0 to infinity because that's the domain of the square root function. So out of these, because of the restriction on g of x, that has to carry through. So this function here, and remember this is the same as the square root of x to the fifth, so that's another way in which we could have written this. The square root of x to the fifth. So because the square root is there, that restriction on the domain is still going to carry. So I have this domain is 0 to infinity. And then I did f times g of 9. So literally just plug in 9, typed this into my calculator. 9 to the 5 over 2 is 243. All right, next one, try a division problem. Again, I think you can do this on your own, so I'm going to let you do this on your own. So pause the video, do the division, f over g of x, identify the domain, and evaluate when x is 16. Pause the video, unpause when you're ready to discuss. Okay, so here, f of x over g of x, which is the same as f over g of x, is literally 6x over x to the 3/4. Now again, here I'm just combining using my properties of exponents. So if I divide the bases, I subtract the exponents. This has an exponent of 1 right here, even though it's not written. 1 minus 3/4. Did that work off to the side again, just to show you the fractions. 1 minus 3/4 is 4/4 minus 3/4, which is 1/4. So I end up with f over g of x is 6x to the 1/4. So this is one form of the answer. But we could also write it as 6 times the 4th root of x. That is the same thing as well. Domain is 0 to infinity. I'm getting that from f of x has a domain of all real numbers because this is a polynomial again, so negative infinity to infinity. But g of x, because this has the 4th root in it, that's a domain of 0 to infinity. So that has to carry through that restriction. And then f over g of 16, plug in 16. 16 to the 1/4 is 2. 2 times 6 is 12. Nice job. Okay, so now we're going to look at this from the graphical standpoint. And remember, this goes back to our warm-up. What does this actually mean? Well, when I add f of x plus g of x, I'm literally adding the y coordinates at every given x point. So here I have an f of x in green and a g of x in red. And I have identified or approximated the y coordinates at given points on both of them. So that's what the numbers in red are representing the g of x y coordinates, and the numbers in green are the f of x y coordinates. So I'm going to add those together. So when I add those together, I get this resulting parabola in blue. And again, literally what I am doing is I'm looking at, okay, well here the green was 1, the red was -1, so when I add those I get 0. Here the red was 1, green was 0, add those I get 1. Here green was 1, red was 3, add those I get 4. Here the green was 4, red was 5, add those I get 9. Notice that the scale of this is 2 if you're confused. Here green and red were both about 6, so that would be 12, which would then be off the graph. And then moving over to the left, so here the green was 4, red was -3, that adds to about 1. Here the green is 6, red is -4, that adds to 2. Here the green is 9, red is -5, that adds to 4. And then this point, I didn't know where the green was here, but I know that the result is a parabola. So by symmetry, if this point was at 9, I also have to have a point here at 9 because now it looks as if my vertex is at 0, 0. So that's what we're doing. So I want you to try to do that for B. So go ahead, pause the video, try to add these two together. Unpause when you're ready to check. My hint is, if you're adding a parabola to a linear equation, the result should still be a parabola. And that should make sense from an algebraic standpoint also, right? If I do x squared plus x, well, that's still a quadratic. So pause the video, add these together. All right, so again, hopefully you got a parabola that looks kind of like this, and here are my numbers so we can see that. 5 plus -9 is -4, 3 plus -4 is -1, 1 plus -1 is 0, 0 plus -1 is -1, -1 plus -3 is -4, and -4 plus -5 is -9. There you go. That is combining functions. Hopefully you had as much fun as I did. I'm sure you did.